Will we conquer space using electric, magnetic, and plasma sails? But what kind of sails are these? Many of you have definitely heard of solar sails or light sails. However, there are concepts of other types of space sails that operate on different principles and could also become a good alternative to chemical rockets for long-distance travel within the solar system, and perhaps even be used to some extent for interstellar journeys. These technologies are very interesting. How about, for example, a sail in the form of a giant invisible field? It sounds like something out of science fiction, and yet it is plausible. Today we'll talk about electric, magnetic, and plasma sails, how they work and how they differ from light sails, what speeds can be achieved with them, their advantages, disadvantages, and much more. I'm Andrei, and this is Cosmos Elementary. The current velocity of the most distant human-made spacecraft, Voyager 1, is about 17 kilometers per second, or about 10.5 miles per second relative to the Sun. Although it is still under the influence of the Sun's gravity and it hasn't fully left the solar system, the environment it's in and its properties closer to interstellar space. It took it almost 50 years to get there. Obviously, this takes a very long time. One might think that it's quote-unquote so slow because it was launched a long time ago. The technology just wasn't as good back then. We can compare it with another spacecraft on a similar escape velocity from the solar system, but launched much later, in 2006, New Horizons. But its current speed is even lower than that of Voyager, less than 14 kilometers per second. But although Voyager is the farthest, it's not the fastest. The current speed record belongs to the Parker Solar Probe. It has already reached speeds of about 176 kilometers per second and can even get to 191 kilometers per second. The Parker Solar Probe has already reached speeds about 10 times higher than those of Voyager 1. So does that mean that if Voyagers had been traveling at that speed, they would have reached their current position not in nearly 50 years, but in just 5? And let's say Neptune in just a year or two. So why haven't we already sent spacecraft to Uranus and Neptune, since such speeds are already available to us? The issue is that the speed of the Parker Solar Probe is, in a sense, deceptive. Now, it really does reach such speeds relative to the Sun, and it's indeed the fastest human-made object in history. But sending a spacecraft into the inner solar system, toward the Sun, and sending it outward into the outer solar system away from the Sun are not the same thing. Let's recall a couple of key points. Given that the Sun is many orders of magnitude more massive than any other object in the solar system, even small bodies like asteroids mostly continue moving calmly in their orbits around the Sun and do not fall into it. Why doesn't the Sun pull them in? Well, of course, it does pull them. It's just that smaller bodies have their own motion. If a planet's orbital velocity were zero, then yes, the Sun would pull it and it would fall into it. But since the very formation of the solar system, they have been in motion, just like the material in the protoplanetary disk from which the planets and all the other bodies formed. To remain in a stable orbit and not fall into the central body, in this case the Sun, an object must have a certain orbital velocity. And importantly, it doesn't depend on the object's mass, but only on its distance from the central body. Jupiter's average orbital velocity is about 13 kilometers or 8 miles per second. Earth's is already 30 kilometers or 18.6 miles per second. And Mercury's is about 47 kilometers or almost 30 miles per second. It is clear that the closer you are to the Sun, the stronger its gravitational pull becomes and the higher the speed must be to prevent the object from falling into it. So when a probe is launched, it first enters near-Earth space into a low Earth parking orbit, and it moves around the Sun at the same speed as Earth does. If we wanted to travel to outer planets like Mars, Jupiter, and so on, we need to give the spacecraft energy so that its orbit is raised. And if we wanted to go toward the Sun, it's the opposite. We need to remove energy from it. We essentially have to slow it down by firing its engines in the direction opposite its orbital motion, which will lower its orbit. And the most counterintuitive thing here is that even though we're slowing the spacecraft down, its orbital speed actually increases. As it gets closer to the Sun, its orbit becomes smaller, and therefore its velocity becomes higher. And that's exactly what was done with the Parker Solar Probe. In addition to using its engines, it also performed multiple orbital maneuvers using Venus flybys. All of this effectively slowed the spacecraft down, allowing it to fall deeper into the Sun's gravitational well. And this is crucial for the mission because its goal is to study the upper layers of our star's atmosphere. As a result, the spacecraft gets much closer to the Sun than Mercury. In short, it moves so fast not because we simply turned on engines and kept accelerating the spacecraft until it reached a speed of almost 200 kilometers per second or about 125 miles per second. And because we are able to slow it down in this way, it, fell closer to the Sun and entered an orbit where any object would move at such high speeds, even if it had no engines at all. Moreover, it doesn't travel at that speed constantly because it is on a highly elongated orbit. When it is at the farthest point from the Sun, it moves much more slowly, while it reaches its record-breaking maximum velocities when it is the closest to the Sun. This animation clearly shows how its speed changes depending on where the spacecraft is along its orbit. In short, it is clear that this trick does not apply to a spacecraft traveling away from the Sun into the outer solar system, because Parker's solar probe speed is determined by its distance from the Sun, not by the power of its engines. But for missions going away from the Sun, we can't get by without more efficient propulsion systems. Although, of course, there are still gravitational assists using planets, which I covered in more detail in a separate video. Examples like Voyager program and much more recent New Horizons show that the speeds we can achieve using chemical rockets are not very impressive. And although we have already delivered spacecraft to the distant regions of the solar system, these are still isolated cases. And to begin a more thorough exploration of the outer edges of the heliosphere, the Kuiper Belt, Neptune and Uranus, or even Jupiter, which is much closer but still takes some spacecraft up to 10 years to reach. It would be great to learn how to accelerate spacecraft to speeds comparable to the Parker Solar Probe, but without using the Sun. And this is where different types of sails could help us, because according to some estimates, they may well be capable of accelerating spacecraft to such speeds. Right now, two main types of engines are used in space, chemical and electric, and both propel a spacecraft using the same basic principle. Propellant is expelled in one direction, and because of conservation of momentum, action, reaction, all that stuff, the spacecraft starts moving in the opposite direction. In chemical engines, the propellant, gas, is accelerated as a result of chemical reactions when the fuel burns. In electric engines, which include ion thrusters for example, the propellant is accelerated by electrostatic effects or magnetic fields. There are significant differences between these two types, and I talked about them in more detail in my video about ion and electric engines. But fundamentally, the principle is the same. We throw something in one direction and we move in the opposite direction. Space sails, however, work on a different principle. Most often, of course, we hear about the light sails or solar sails. In fact, those are usually the only kinds we hear about. And that's not surprising, light sails do have their advantages. Most importantly, it is the most mature technology. Working prototypes have already been built, spacecraft with light sails have already been launched into space, and it has already been demonstrated that yes, they do work. About light or photon propulsion in general and about light sails in particular, I've already gone into detail as well, so we won't dwell on them here. I'll just briefly say that they work thanks to the radiation pressure. We need a large, thin, reflective sail. Sunlight or laser beams interact with it and push the spacecraft into motion. It's almost like wind driving a sailing ship on water. Many people find this confusing. How can light act this way if photons have no mass? They don't have mass, but they do have energy and momentum, and they are fully capable of transferring that momentum to a sail and setting a spacecraft in motion. If you're still unsure about this, I talked about how it works in detail in a separate video about a black hole made of light. But with the sails we're talking about today, people are much less likely to have those kinds of doubts. Here, instead of photons, the motion would be driven by the solar wind, which consists of very much massive particles that stream through the solar system at high speeds. You can even argue that the term sail is more appropriate here because We are literally using wind, just solar wind. The sun constantly emits a stream of charged particles in all directions, mainly protons and electrons. These particles travel at speeds of up to 750 kilometers or over 460 miles per second. They have mass and momentum, and if they interact with the sail mounted on a spacecraft, these particles transfer their momentum to the sail and the spacecraft, causing it to move. This really is similar to the principle of a conventional sail, except that instead of air particles, we have charged particles of the solar wind. And another difference is that the interaction would not occur through direct physical contact, but rather through charged particles interacting with the electric and magnetic fields generated by the sail. At the core of electric, magnetic, plasma, and other variations lies the same fundamental principle, but the details of how exactly momentum is extracted from the solar wind differ. One of the advantages of all types of sails is that this is a propulsion technology that does not require expelling propellant. In some cases, this solves one of the main problems of chemical engines, the need to carry a large amount of fuel for chemical reactions and mass expulsion. We need the sail itself and a source of energy to launch it and/or sustain its operation. Electric sails, as one can guess from the name, generate an electric field. The sail itself doesn't even really look like a sail. It isn't continuous like a traditional or solar sail, but instead consists of several separate, extremely thin wires. It reminded me of the game MDK, where the character had a parachute that was made up of separate thin fragments. Hit that like button if you're old. As an example of such an approach, we can consider a specific project, HERTZ, which has already received a grant from NASA under its Innovative Advanced Concepts program. HERTZ stands for Heliopause Electrostatic Rapid Transit System. The basic principle of how it works is as follows. The sail consists of about 10 to 20 essentially bare wires, each of which, depending on the configuration, can be anywhere from 1 to 20 kilometers long. At launch, the wires are coiled up, and once the spacecraft reaches space, it spins out and the wires become taut. Then voltage is applied to the wires. The idea is that the electrostatic field created around them will deflect the charged particles of the solar wind, and in doing so, these particles transfer their momentum to the sail. But someone might have noticed a little problem here. I said that the solar wind consists of protons and electrons, and they are present in roughly equal proportions. Because of this, another important element is an electron gun. The wires need to be kept at a positive charge so that they repel the positively charged protons. The electrons in the solar wind, on the other hand, are attracted to the sail, and in order to prevent the charge from being neutralized, electrons are emitted by an electron gun. In effect, protons push the sail like this. As I know, there's magnetic fields rather than electrostatics, but the idea is similar. Like charges repel each other. The wires are very thin, about 25 micrometers in diameter, which is comparable to a very thin hair. They can also be made of separate segments of different lengths, soldered together, in order to reduce the risk of failure when colliding with micrometeoroids. The electrostatic field created around the wires spreads tens of meters in all directions, and as the distance from the sun increases, it can only expand further. Which is better, an electric sail or a light sail? It might seem that a light sail is simpler in this respect. At least in order to propel the spacecraft at all, the sail itself does not need any energy after deployment. There's no need to deal with positive and negative charges. But still, if we look at the proposed design of the electric sail, it seems simpler as well. For a light sail to be efficient, it must be very lightweight, extremely thin, highly reflective, and most importantly, enormous in surface area. An electric sail is just a few dozen wires, and in theory, it should be easier to manufacture as well as to deploy in space. Here, the main surface area of the sail is actually the invisible electrostatic fields. Another aspect where the solar sail might initially seem to have the advantage is that, somewhat surprisingly, the pressure of sunlight is higher than the pressure of the solar wind. There are fewer solar wind particles hitting a given area than photons. And yes, they do have mass, but they also move much more slowly. But the key point is, it all depends on the distance from the sun we're talking about. And both the pressure of sunlight and the solar wind decreases as you move farther away from the sun. However, when a spacecraft with a solar sail moves out to about 5 astronomical units from the sun, roughly the distance of the asteroid belt. The acceleration produced by solar photons becomes almost negligible, and the acceleration from the solar wind remains effective much farther out, more precisely, up to about 6 times farther. Here is a comparison graph of the thrust of the two types of sails at different distances. Here is the thrust of the electric sail, and here is the light sail. It is obvious that with an electric sail, the spacecraft continues to accelerate for much longer. Plus, the physical size of a solar sail doesn't change, whereas the effective area of the electric sail's field, as I mentioned, increases with distance from the Sun. The charge on individual wires can also be controlled, allowing the sail to be adjusted in this way. By orienting it in a certain direction, it can not only raise the orbit, but also lower it and even send the spacecraft inward toward the inner solar system. Electric sails are also advantageous because they can be used to reach orbits that are strongly inclined relative to the plane of ecliptic. Solar wind blows in all directions, and in theory it could be even used to place spacecraft into retrograde orbits. Of course, chemical propulsion and gravitational assists can also tilt an orbit, but again this requires fuel that has to be carried along. Here, however, you can simply orient the sail in a specific way. An electric sail can accelerate a spacecraft up to about 100–150 kilometers or about 60 to 93 miles per second. And this would no longer be a speed determined by proximity to the Sun, like in the case of the Parker Solar Probe. At this speed, the spacecraft would actually be moving away from the Sun. In principle, even higher velocities are possible. Of course, there is also some nuance. If we rely on the solar wind, such a sail would be much less efficient or potentially even ineffective inside planetary magnetospheres, where the solar wind is deflected and significantly weakened, because a strong magnetic field deflects a significant portion of the charged particles of the solar wind. Another nuance is that the solar wind is not constant, and it can change depending on solar activity. In practice, if we were building such a spacecraft, we would need to take this into account, using specialized algorithms, predictive models, and continuous monitoring of the Sun's activity. Another advantage of a light sail is that we are not limited only to the Sun. We can also build powerful lasers ourselves that would accelerate the spacecraft. This idea is the basis of the Breakthrough Starshot project, which I have mentioned before, and within which there are plans to eventually send a swarm of microprobes to the Alpha Centauri system. Well, since we're talking about interstellar flights, we can also allow ourselves to imagine and picture what if we built an interstellar spacecraft with such an electric sail. Of course, it would still take a very long time to reach another star system. Tens of % of the speed of light are not on the table here. But still, at least it could, upon arrival, brake using the stellar wind of the target star in the new system. What state is this technology in right now? Well, here it falls behind the solar sail. As I already said, there have been NASA grants for development, there are paper stage projects, there have been laboratory experiments in which the effectiveness of such wires creating an electric field was tested. Here is a photo of such an experiment. The next step is testing the technology in space, and attempts have already been made. In 2013, the first Estonian satellite in history, EST-CubeOne, was launched. It was a CubeSat or a small satellite. One of its tasks was to test an electric sail. The satellite carried electron guns as well as the sail itself. However, instead of using multiple wires, it used just a single short one, only 10 meters long. The efficiency of the electric sail was to be evaluated by measuring how the satellite's rotation rate changed due to the interaction between the sail and the charged particles in Earth's ionosphere, rather than solar wind particles. In addition, the sail's effect could also cause the satellite to deorbit more quickly. The satellite was placed into orbit, communication was established, and it sent back images of Earth. However, the sail's wire could not be deployed. The reel may have gotten stuck. As a result, the sail could not be tested. But they didn't stop there. A second attempt followed with the EST-CubeO satellite, but this time as well it was unsuccessful. Apparently, it failed to separate from the launch vehicle and burned up together with it in the Earth's atmosphere. There was also ALTA-1 satellite. It was launched, but it failed to deploy its wire. In 2022, the Finnish satellite for Sail-1 was launched. It already had a 60-meter wire and was also intended to test the operation of an electric sail in the ionosphere. However, contact with it was lost a couple of months after launch. Overall, it's been a series of failures when it comes to testing electric sails. It might still be possible to carry out full-scale space tests within the EST-3 or 4-sail 2 missions, but for now, that's the situation. But we still have magnetic sails. How are they different? Besides the electric field interacting with charged particles of the solar wind, a magnetic field can also interact with them. And magnetic sails use this principle. It might seem like there is no real difference. Charges here, charges there, fields here, fields there, but in reality, these are two very different physical mechanisms. If you rub a pen against your hair, it builds up an electrostatic charge and can attract small pieces of paper. A magnet also attracts and causes motion, but in this case it's a magnetic field. Although of course electric and magnetic fields are closely linked. One can generate the other. And both are manifestations of a single fundamental interaction, electromagnetism. There are also different types of magnetic sails. One of the earliest, if not the very first concept, is called mag sail, which is short for magnetic sail. Here's a very schematic view of such a sail. It may look similar to an electric sail, but here the wires are not actual conductive tethers. They are only structural elements supporting the large ring, and it is that ring that generates the magnetic field. The ring unfolds when a spacecraft is already in space, and it has to be enormous, tens of kilometers or miles in diameter. How will it generate a magnetic field? Inside the ring, there are superconducting wires. A current is applied to them, and a magnetic field is created around the ring. In effect, it's a gigantic electromagnet. The interesting point here is the following. The ring is not chosen to be superconducting by accident. If a material has superconducting properties, it has zero electrical resistance. And when current is first applied to the ring at the beginning, there is no need to keep supplying voltage afterwards. The current will continue flowing through the superconducting wires for as long as desired. And that's very convenient, though some technical difficulties may arise here. Yes, we already know how to create superconductors, but they require extremely low temperatures to work. You might think, great, we're in space, and it's cold there anyway. But it's not that simple. Actually, I made a whole video about the question of temperature in space. In short, in space, an object can both cool down significantly and heat up. For example, when it is directly exposed to sunlight. In short, for such a magnet to work properly, you also need a pretty good thermal regulation system. So we create a huge magnetic field around our spacecraft. And again, the stream of charged particles will be deflected by the field. In this way, momentum will be transferred to the sail, thrust will be generated, and the spacecraft will accelerate. Such a ring can operate in different configurations. The ring can be oriented both parallel and perpendicular to the particle flux. The advantage of such a sail over a light sail is again that the structure of the sail itself can be much smaller, while the effective area remains very large. There's also another interesting aspect. A magnetic sail can interact not only with the particles of the solar wind, but also with the magnetic fields of planets. And in space travel, this could introduce a new type of maneuver. In addition to long-used gravity assists, where a spacecraft uses the gravitational field of a planet, it flies past along a special trajectory to accelerate or decelerate. Magnetic maneuvers or magnetic assists may also become possible. In the same way, a spacecraft could gain additional acceleration or deceleration by flying through the magnetic fields of planets. In the solar system, Earth, the giant planets, and even the Sun itself could potentially be used for this purpose. The theoretical speed limit here is the speed of the particles on the solar wind. So at the maximum, somewhere around 700 or 800 kilometers or 430-500 miles per second. But looking at it more realistically, the speeds would probably be comparable to those of electric sails, roughly around 100 kilometers per second, give or take. Of course, a lot depends on the design of the spacecraft and the sail itself, and the specific mission. Although the structural part of a magnetic sail may be smaller than that of a light sail, a ring tens of kilometers in diameter is still a bulky structure with considerable mass. But what if we could do without the ring altogether? In essence, this could potentially be achieved through the concept of a plasma sail or a plasma magnetic sail. Here, there are no extended wires or giant ring at all. Instead, an invisible magnetic bubble is created around the spacecraft. which also extracts momentum from the solar wind. This sounds even more futuristic. How is it supposed to work? A relatively small electromagnet is installed on the spacecraft itself. In the original concept, a device with a mass of only 50 kilograms was proposed, and it would not require much power, about 3 kilowatts. This magnet creates a small magnetic field around the spacecraft, but this alone is not yet a sail. Then plasma is injected into this field in a specific way from the spacecraft. Since plasma obviously consists of charged particles, its motion can also generate a magnetic field. The plasma injection essentially amplifies the original magnetic field, causing it to grow in size. As described in scientific papers, this process effectively inflates a kind of a magnetic bubble created by the electromagnet. It could expand to tens of kilometers across. And just as our Earth is surrounded by a magnetic field, here too it is surrounded by a similar field, only a miniature version of that. At this stage, these are still theoretical studies and simulations. Not all authors agree on how much thrust such a sail could actually produce. In practical tests so far, experiments have been carried out in laboratory conditions on Earth, where it was confirmed that plasma injection can indeed amplify a magnetic field, and it does. However, the amount of thrust that could be actually achieved in such a system has not yet been experimentally verified. By the way, another interesting potential side effect, although arguably a positive one, of creating magnetic fields around a spacecraft is protection from cosmic radiation. After all, it poses a threat both to living organisms and to onboard equipment, and such a magnetic field could act as a kind of shield, deflecting high-energy charged particles. In my video about cosmic radiation, I mentioned that magnetic fields are considered as a possible option for such protection. And as I've already mentioned, there are different variations of sails. There's also not just electric and not just magnetic, but electromagnetic concept, in which both approaches are essentially combined, and both electric and magnetic fields are used to generate thrust. There's also another combination. On a single spacecraft, two propulsion systems could be used simultaneously to generate thrust, an electric sail and an electric engine, such as an ion thruster. In this setup, they would complement each other. It all sounds very interesting, and most importantly, it doesn't require any fundamentally new technologies. The operating principle here is quite well understood, although we need to keep in mind quite a few aspects. All of this still needs further research, and of course, real prototypes will have to be built and tested in space. It is quite possible that in a similar way to how ion and other electric propulsion systems are becoming increasingly used today, space sails will one day find their place as well. However, chemical rockets are still unavoidable for now. Launching spacecraft from Earth's surface using such systems is not really feasible yet. The vehicle first needs to be placed into space, and only then can the sail be deployed to travel to the distant regions of the solar system and explore them, and perhaps one day even interstellar space. Thanks for watching. Links to all of the sources are, as always, down below in the description, and if you enjoyed the video, don't forget to like, comment and subscribe for more videos in future. Bye.